So, good morning, everybody. I will continue on the chapter about mortality. And in the previous class, we saw the general concepts related to mortality. And now we will enter this topic on the standardization. The idea is that when we want to compare mortality levels of countries or populations that have different age structure, we cannot use the crude death rate. The crude death rate is that simple indicator that we just get the total amount of people that died in a specific year in a specific population divided by the population, the total population of that place, and multiply by 1,000. In this case, the crude death rate is not calculating different chances of dying by age groups. And we have to take into account different chances of dying, different risks of dying by age groups, because mortality is much higher among older people, and also infant mortality is higher than little older kids. So we have to take into account these different chances of dying across ages. And by doing that, we are able to compare mortality levels of populations that have different age structures. What does it mean, age structure, age composition? Some populations might have a higher proportion of people in younger ages. Others might have higher proportion of people in labor ages, others in elderly ages. So we have to take that into account. Because if we simply compare populations with different age structures, their crude death rate, countries that have a higher proportion of people in older ages probably will have higher crude death rate than countries with younger age structure. So one way to do this comparison, to take into account age composition when we are trying to compare mortality levels and experiences across countries, is to use standardization. And standardization takes into account age composition when we compare death rates among countries. And we pretty much will generate a new crude death rate. This new crude death rate will be able to compare with the other country that we are trying to understand the comparison here and see which one has the highest levels of mortality. So if we have the crude death rate, for example, for the US, and the crude death rate for Venezuela, the original ones, it's not appropriate to compare because a higher proportion of the population in Venezuela is younger, lower chances of dying. Opposite of the US, higher proportion of people in older ages, higher chance of dying. So we generate a new crude death rate for Venezuela in order to compare to the US. Or we could do the opposite, generate a new crude death rate to the US to compare to Venezuela, right? And this exercise of generating this new crude death rate is the standardization technique that I'm going to show you here now. So we pretty much will adjust for differences in age structure. And what we will do basically is estimate age-adjusted death rates and apply it to a standard common population with similar age distribution. But you could tell me, I mean, what about why you just don't do to mortality the same way as you did for fertility? Remember how we calculated total fertility rate? We got the age-specific fertility rates, how many kids women had in a specific year, divided by the number of women, but for each one of these 5-year age groups, right? And we had women between 15 and 49 years of age, but we subdivide them in these 7 5-year age groups. And we got these age-specific fertility rates and multiply by the width of the age interval, which is 5, add everything, and calculated the total fertility rate. And the total fertility rate, how do we interpret it? If we expose a group of women to these fertility rates by age groups throughout their lives, they would have on average this amount of children, right? Throughout their reproductive ages between 15 and 49. Why can't we just do something like that? Get the age-specific mortality rate for each one of the age groups, multiply by the width of each one of the age groups. The age groups can even have different widths, but just apply the specific one for those, and then you would have kind of a new indicator called the TMR, the total mortality rate. Why demographers don't use the TMR? This TMR doesn't exist. Why people don't calculate the TMR, the total mortality rate? Because how would you interpret the total mortality rate? If people were exposed to the chances of dying measured by the age-specific mortality rates throughout their lives, they would die so many times. That doesn't make any sense, right? Because we die just once, right? Since we die just once, we cannot estimate a mortality indicator analogous to the total fertility rate. We cannot say, oh, if a hypothetical group of people was exposed to the chance of dying as measured by the age-specific death rates here, they would die on average 1.5 times, 2.1 times. So since that doesn't make any sense, demographers had to come up with some other measures that would take into account the age composition of the countries and be able to compare the mortality realities of these countries. So with the age standardization, that's exactly what we try to do. Because young populations, they tend to have low crude death rates. Young populations, like higher proportion of people below the age of 64, those people are less likely to die than older people. So in a specific year, overall, you might have, even proportionally to the size of the overall population, lower crude death rates than other countries, more developed countries, for example. In countries, exactly more developed countries, where mortality is actually declining, people live longer, they have older populations, higher proportion of people with at least 65 years of age, they will tend to have higher crude death rates because you have a lot of people die in a specific year because more people are close to the ages with higher chances of dying. So what we discuss here is an adjustment of the crude death rate, a variation of the crude death rate that allows us to account for age composition when comparing death rates across different populations, different countries. We pretty much get the age-specific death rate of a specific country and multiply it by the proportion of people from this other standard population, right? It's kind of like we are applying the mortality of one country to the population of another country. If I have the US, the age-specific death rate of the US, it's already applying to the population of the US. And if I get the age-specific death rate of Venezuela, is applying to the population of Venezuela. So I can get the age-specific death rate in Venezuela and say, oh, let's expose the American population to these rates here. How many would die? And then we can compare this new measure to the original one from the US. Or we could do the opposite as well. So that's the exercise, right? So I will just go now here, step by step, to explain how to do it. So this is the data for the US. What data do we need to do this analysis here? We need the population by age groups, and we need how many people died in a specific year in the US by the same age groups, and everything from the same year. What information did we have when we calculated the original crude death rate? We just had these two numbers here. 2.5 million died in the US in 2006 in a population of around 298 million people. Divide one by the other, divide this number by this number here, multiply by 1,000, we have a crude death rate of 8.41, which means that for every 1,000 people in the US back in 2006, we had 8.4 deaths. Now we need more detailed information. We have to break it down by age group. And as I said before, the first age group, we subdivided from 0 to 1 and 1 to 4, because the chances of dying before reaching age 1 is much higher among these babies. So we calculate that, separated from 1 to 4. And the last age group depends on the availability of data. Some countries might not have reliable data for 100 plus. We might see estimations using 80 plus or 85 plus, so that depends. But if I'm comparing two countries here, I have to at least get same year and information of population and deaths for the same age groups. For the US is this one here. This column of proportion of population, I'm pretty much getting 4.1 million divided by 298 million. So we have 0.014 of the population there. In percentage terms, we are saying that we have 1.4 of the US population between the ages of 0 to 1, or not completing age 1. 5.48% between the ages 1 and 4, and so on. How many deaths happen? And if we get these deaths here and divide by the population, we get the age-specific death rate. All right, so the age-specific death rate from 0 to 1 is 0.006, drops a lot to the next age group, 0.00029, and it's low and then starts to increase as people get older, and really high among older ages. What's the similar data in this example for Venezuela? Same age groups, same year. We have the population and the deaths. If we just get the overall death and the overall population, divide one by the other, divided by 1,000, we get that for every 1,000 people in Venezuela back in 2006, 4.6 died. Wow. Look at that. Previous, 8.4 in the US. Venezuela, 4.6. Does it mean that mortality is lower in Venezuela than in the US? We cannot compare mortality between the US and Venezuela with these original crude death rates because they are not taking into account age composition. They are not taking into account this column here. So here for Venezuela, 487,000 divided by 22.2 million, we have 2.19 of the Venezuelan population here. And then you're going to see that these numbers here in younger ages for Venezuela are higher than for the US. And these numbers here, the proportion of people in older ages in the US is higher than in Venezuela. It's hard to see comparing these two tables, but I will show some graphs that makes it clear. And now, since we have deaths and population by age group, we can calculate the age-specific death rates. This number by this number, we have the death rate for this age group of 0.01623. And if we multiply by 1,000 here, we are saying that for every 1,000 people, children between the ages of 0 and 1, 16 are dying. Out of 1,000, 16 are dying in Venezuela. and only 6.5 in the US, according to this data. 6.5 out of 1,000. The US, 16 out of 1,000 Venezuela. That's why we have to take this into account, because the chances of dying seems to be higher in Venezuela than in the US, which the crew death rate is not capturing. So just to show how these countries have different age structures, I just get this column here, population proportion, and multiply it by 100. So this 0.0219 is the 2.19 here. The 0.0800 is the 8% here, so it's the same number. But now instead of adding to 1, it adds up to 100%. Here's because of rounding problems, but adding to 100%. And then you're going to see that in the US, we have lower proportion of people in younger ages compared to Venezuela, and higher proportions or higher percentages of people in older ages compared to Venezuela. Just to make this even more clear, we can divide this percentage here by this percentage. We have the ratio of these percentages of population by age group of the United States to Venezuela. When these numbers here are below 1 unit, so US is in the numerator, Venezuela in the denominator. If it's below 1 unit, we have more people in Venezuela. If it's above 1 unit, we have more people in the US. So we see that we have more people proportionally in the US in older ages. So the US has an older population than Venezuela. This is causing the crew death rate in the US to be higher than the crew death rate in Venezuela. So we have to deal with this issue. This graph here is just putting these two columns in this table into a graph format. It's easier to see, right? We have the US in blue and Venezuela in red. And we have a higher proportion of the Venezuela population in younger age groups and a higher proportion of the US population in older age groups. 40 plus is higher, the proportion of people in the US than in Venezuela, and below that is higher in Venezuela. And if we get this column here and put in a graph format, we have this line here. And 1 is just a reference. If this ratio is below 1, we have more people in Venezuela than in the US. Again, why? Because Venezuela is the denominator here in this formula. More people here, the ratio will be below 0. More people in the US, this ratio is going to be above 1. And that's exactly what you see in this graph. So we have to take into account this different age structure, right? And going back to the first tables, we get now the age-specific death rates of Venezuela and the age-specific death rates of the US, and put in a graph format. Put it here. So what we see is that for all age groups, the chances of dying is higher in Venezuela than in the US. Here in the middle, you don't see that much difference, but just because of the scale of the graph. In Excel, I just put some examples that I zoom in to these specific age groups here, and you see always the chances of dying in Venezuela higher than in the US. The red line higher than the blue line, right? Okay, so we have a problem. We have a problem because the composition of Venezuela is different than the US, is much younger, and that is making the crew death rate in Venezuela being lower than in the US. So let's standardize the Venezuela crew death rate by saying, like, let's get the age-specific death rates of Venezuela, the observed ones, and let's get those rates and apply to the US population. So the US population will be the standard population in this case. What we are saying is like, let's get the rates, the chances of dying in Venezuela into this older population. Let's see if this older population of the US, how many people will die if they were exposed to the mortality in the US. So you pretty much get the rates from Venezuela and multiply by the proportion of people in the US by age groups, which is our standard population. We just multiply one by the other, add this all, and multiply by 1,000. Look at that now. The crude death rate of Venezuela, if we have those chances of dying in Venezuela applied to the older population in the US, 9.68 people will die out of 1,000 people. What did we just do here? We just implemented that formula that I showed you before. This formula here. We get the age-specific death rates in Venezuela by age group, multiply by the proportion of people in each one of the age groups from the US. We add them all, and then multiply by 1,000. This is exactly what we did in this table here. Get the observed rates by age group, the proportion of the population in the US by age group, multiply one by the other one at a time here, add them all, and multiply by 1,000. 9.68. Originally, let's just go back. I have the summary slide afterwards, but just go back. Venezuela, 4.6. The original crude death rate in the US, 8.4. Original crude death rate in Venezuela, 4.6. 4.6 go to 9.6. If I get the chances of dying in Venezuela and standardize the population that will be subject to it, right? I'm pretty much holding constant the age composition. And this is the same idea that we had before. It's just another way to implement the same exercise. In this case here, instead of having the proportion of people in the US by age groups, we have the original numbers, the number of people that we had in the first table. If these people here were exposed to these age-specific death rates in Venezuela, we would have 67,325 deaths in that age group. And then we add all these guys here, we add all these guys here, divide one by the other, multiply by 1,000, we get the same 9.68. So what do we have in summary? The crude death rate in the US, the original one was 8.4. Venezuela was 4.6. And you say, wow, mortality is higher in the US. But you have to consider that the US has an older population. So let's get the rates of Venezuela and expose the US population to that chance of dying. The Venezuelan crude death rate increases to 9.6. Now we can compare this 9.68 to 8.4 because the standard population is the same as the US. And the crude death rate that we had originally from the US is already using the US population. We could do the opposite as well. We could estimate a new crude death rate for the US using the Venezuela population as the standard, right? Here, just do the opposite. So that's this part about standardization. And as I told you in our course website, just go to our course website. I have some Excel files saved there that I suggest you looking at them, just to show you exactly the mortality chapter here. Example of standardization. an example of light table that we're going to talk next. Example of standardization, if you download this as a compressed file, and then you're going to get this file here, Standardization USA Venezuela. If you open this file, it's pretty much the same tables that I showed in the PowerPoint. I just did all this calculation in Excel and transported to PowerPoint. So here we have the first table for the US and Venezuela, 8.4 crude death rate for the US, 4.6 for Venezuela. And then here we see the age-specific death rates are higher in Venezuela than the US. If we just look at people between 0 and 29, because here it's hard to see these differences here, 0 to 29. Let's just look at closer, then you see that Venezuela is higher than the US. Maybe closer between ages 1 and 4, but it's still higher. And if we expand a little bit from 0 to 39, you also see higher in Venezuela than in the US. And then only for the older groups, 45 to 100, higher in Venezuela as well. Here kind of close as well to the rates in the US, right? And then what I did next, I just got this proportion here and calculate the percentage, the same thing. So it's just this number multiplied by 100. And I have these two new columns. And if I just plot them, I see, so this graph here is using exactly this data. And these rates here that we saw before, it's using the data about the age, where did I, it's not selecting there, but it's using these two columns here. The age-specific death rates are the ones generating this graph. And for these other graphs, I get these numbers here, percentage of people by age group in the US and Venezuela, and I calculate this. I generate this graph. That we see higher proportion of younger people in Venezuela than the US, and higher proportion of older people in the US than in Venezuela. If we get the ratio, this is the graph that I use for the ratio, and I put 1 as the reference, so I use this column here as well. And then I apply the formula that I showed in this slide, and it appears in the textbook. I get the rates of Venezuela, getting from column L, the standard population of the US, proportion of people in the US by age groups from column D, multiply one by the other, add everybody, and then I multiply by 1,000. So I pretty much got the rates from Venezuela from column L and the proportion of the population in the US from column D to calculate the crude death rate of Venezuela standardized by the US population. So now we have exactly those numbers. Your regional from the US, or regional Venezuela, but when we apply the chances of dying in Venezuela to another population, 9.6 is higher than 8.4. And this is that other way to do it. You just get the count of population in the US, which is our standard population, the observed rate, multiply one by the other, add this all. It's going to tell you how many people would die if this US population was exposed to the chance of dying in Venezuela. Divide this number by this, multiply by 1,000, you have the crude death rate that we just estimated. This number here is the same as this. Whatever you think it's easier to understand, you can do the same, get into the same result, okay? All cool? So now we have a way to compare mortality trends of countries that have different age structure, because we cannot calculate that total mortality rate, that indicator that doesn't exist, because that would not make sense. Another indicator that I will show you here that estimate mortality levels and allow us to compare across countries is life expectancy, right? The life expectancy, we pretty much are also taking into account different age compositions of these countries. So we get their age-specific death rates, the ASDRs, the age-specific death rates, the death rates by age group of these different populations, and we apply the same number of people being exposed to those chances of dying, and then we come up with this new measure of life expectancy. And we have life expectancy for several age groups, which I'm going to go in detail here now. How do you calculate the life expectancy? You calculate it with the use of life tables. And I'm going to show the calculation of a life table of life expectancy in a life table in Excel. Some people might do life tables in other statistical software packages. I will do here in Excel as well. That's the one that you can download from the website. One of the most important and elegant measures of the mortality experiences of population is the life table. It actually dates back from the same John Grant, the father of the demography that we already discussed. Demographers use the life table to determine life expectancy. And we have a life expectancy at birth for the first age group, but the life table generates a life expectancy for all the other age groups, with the idea that if I expose a group of people to the age-specific death rates of this country from this year, how many years on average I would expect these people to live throughout their lives. So that's what the life expectancy gives us. And this measure that I gave you is the life expectancy at birth, the one for the first age group, 0 to 1. But let's say that I survive up to the age 20. When someone survives up to the age of 20, that person overcame the risk of dying earlier and did not die. By that person not dying before the age 20, when that person reaches age 20, that person will have some remaining expected years of life. And the 20 plus this expected remaining years of life will be higher than the life expectancy for the age group 0 to 1, because that person already overcame the risk of dying. So the life table is interesting because it gives us all these life expectancies for all these different age groups. And we're going to discuss and give examples in these coming slides. So like the total fertility rate, the life table is a synthetic or hypothetical measure. It tells us how many years of life on average may a person expect to live if the person during his or her lifetime is subjected to the age-specific probabilities of dying of a particular country or population at a given time. Let's remember the Lexis diagram. We have here the Lexis diagram with, just see if it's within this screen. Yeah. We have here time in the horizontal axis, and we have age in the vertical axis, right? When we get information about age-specific death rates for a specific country, we are getting that for in one specific year, like in this example for standardization. We got it from 2006 for Venezuela and the US. So we go in a specific time point and we get how many people died and how many people are in total in each one of these age groups here. So for each one of these age groups, we know how many people died and the population in that age group. So we have the DXN divided by the PXN in each one of these age groups. When we get this number here to calculate the life table, we are again doing that exercise of a synthetic cohort. of a hypothetical cohort. What does it mean? For example, if someone here, let's say that here we have 10, someone is 10 years old. When that person reaches the next age group of 15, this is not going to be the chance of that person dying. The chance of the person dying who is now 10 in this specific year, when that person reaches 15 years of age, will be here 5 years later. So when we create a measure of mortality using just one single year, we are actually doing this exercise by saying that let's expose this hypothetical cohort to these chances of dying, to these age-specific death rates. So we are pretty much getting this period measure and kind of applying it to a cohort. Let's put this number here. This one is going to go inside here, and so on. This number is going to go here, this number here, this number here, here, and here. So we're kind of saying, okay, let's just imagine that some people were born here and they were exposed to these chances of dying throughout their lives. Is that a real cohort? No, it's not a real cohort. Because, like I said, this person who has this chance of dying at age 10 is not going to have this chance of dying at age 15. It's going to be the chance of dying 5 years later because mortality keeps improving. So that's a hypothetical measure. We are getting the age-specific death rates of a specific population, a specific year, and applying to this hypothetical group of people and saying how many years on average those people live if they were exposed to these chances of dying throughout their lives, from age 0 until 80 plus or 100 plus, depending on the data. So that's the overall strategy that we use here to calculate the life expectancy for all age groups, right? So that's this exercise of a hypothetical cohort or synthetic cohort, a cohort that doesn't exist, and I'm getting data from the period to generate an indicator to analyze the overall level of mortality in that country. So let's say that the population of the US in 2010 had a life expectancy at birth of 78.7 years. What does it mean? This means that if a cohort of people throughout their years of life, remember the Lexus diagram here, were subjected to the age-specific death rates, the MXN, they would live on average 78.7 years. That's what it means, right? And we can just see some examples of life expectancy at different parts of the world, back with data from 2013. Of course, we have much more recent data, but here's just to say that there is variation. The world life expectancy among men was 69 years old back in 2013, 73 for women, higher in more developed countries, lower in less developed countries, except taking out China here because the population be so big, it can bias. Japan, the highest life expectancy in the world, and Lesotho and Sierra Leone here, examples of the countries with one of the lowest life expectancies in the world. So you see variation across countries. You know that, for example, the population in Sierra Leone, you have a higher proportion of people in younger ages, and compared to Japan, who has a higher proportion of people in older ages. But we can compare these two numbers, 80 and 45, because we are taking into account age composition. We are taking into account the age-specific death rates to calculate the life expectancy. And as we always talk, women on average live longer than men. In all cases here, that's what we see. So we calculate life expectancy by sex, right? And yeah, this one here, to be more specific, is the life expectancy at birth. If people were exposed to the age-specific death rates for all the different regions here, for the world, more developed countries, or for Japan, and so on, they would live on average this amount of years among men and among women. So before we start, it's just good to explain some limitations of the life expectancy at birth. And life expectancy at birth is symbolized by the E0. We need to be aware to the fact that when considering life expectancy at birth, the infant mortality plays an important role on the level of life expectancy at birth. When life expectancy is low, a major reason is their very high infant mortality rate. For some countries, you might get really low life expectancy at birth, like we saw here in Lesotho and Sierra Leone. In some cases, we are pretty much, when we compare, like in this graph here, Sierra Leone and Japan, we might be seeing these really drastic differences because of infant mortality in Sierra Leone being much higher than in Japan. So just to see if it's not just infant mortality, but other mortality in other age groups, we can compare the life expectancy between these two countries in older age groups. So in the Alexis diagram, once someone reached this age or an older age, it, like I said before, it had the chance of dying before, it did not. So now we'll gain some bonus years of life because they did not die before. So maybe it's better to compare the life expectancy of these countries that have really despairing infant mortality, the life expectancy at the group 1 to 4 or 5 to 9, for example. And when we compare the values of life expectancy at birth across countries, we should not think of the life expectancy at birth as that age in which most people die. Not necessarily most people in Lesotho and Sierra Leone, most men are dying on the ages of 42 and 45, and women in the ages of 45 and 46. Because since infant mortality is so high, that can make life expectancy at birth declines a lot, but once people reach the next age group, they regain some bonus years of life. So that 42, 45, they will overcome those numbers really easily if they reach at least 1 year of age, right? It's just a overall understanding. This is really important when you are trying to understand levels of mortality in countries with really high levels of infant mortality, which is not the case of the US. When we do life tables, we calculate what are called the abridged life tables, which pretty much is a life table by age group. The same way that we did for total fertility rate, that we get information of births and of women by age groups. For mortality, we do the same thing. Those same age groups as we saw in the standardization exercise. And in this case, we usually have 5-year age groups instead of single-year age groups, because information for single-year age groups is not reliable for a lot of countries. But we do subdivide the first age group from 0 to 1 and 1 to 4 exactly to capture infant mortality. When basically what we need for to calculate a life table is to get the number of people who died in a specific year, in a specific country by age group, and the population in each one of these age groups. Dividing one by the other, we have the age-specific mortality rates. And then we just implement a formula that transforms the age-specific mortality rates into age-specific mortality probabilities. So age-specific mortality rates, the denominator of the formula is the population, the mid of the period. Age-specific mortality probabilities, the denominator is the population at the beginning of the period. It's just adjustment that we do it in order to calculate the life table correctly. So now we have the age-specific mortality probabilities that we calculated from the age-specific mortality rates. Now we will apply this mortality probabilities by age groups into a group of people. This group of people who will hypothetically be born in this year in this country and be exposed to these mortality rates, and more specific to the mortality probabilities. And the number of people that are born in this exercise and will be exposed to these chances of dying in the life table is the red X. The red X is the little L0. I mentioned to you before the little L0 in the chapter about fertility is the number of people who will be exposed to those chances of dying. And this number is arbitrary. And the convention is we usually use either 100,000, 1,000, or 1. So if we have the age-specific mortality rates from one country and for the other, we transform them in mortality probabilities, and then we get the same population of 100,000 or 1,000 or 1, and apply that chance of dying. Do these calculations to the end, have the life expectancy estimated for that country. From each age to the next, the population is decremented according to the age-specific mortality probabilities until all members have died. The mortality schedule, or the mortality by age group, is fixed and does not change over the life of the population because we have this hypothetical cohort. We are saying that this mortality here, the chance of dying is going to be that one from the years that they are born until the year that everybody dies. Okay? So this is example in the textbook. So this column 2 here is the symbol for the mortality probability by age group. The QXN is the age-specific mortality probability. Remember that we were talking before about mortality rate. Example from the US and Venezuela. What did we have? Population by age group in one column, people dying by age group in the other column. Divide one column by the other, we have the mortality rate by age group. I'm going to show you, we're going to make a transformation from this mortality rate by age group. We're going to get the mortality probability by age group. Which age groups? Exactly those same ones, 0 to 1, 1 to 4, until the final open-ended interval. In this example, 100 plus, it can be 85 plus, 80 plus, depending on data availability. This is the life table. I'm going to show you an example, for example, in Excel that has many more columns, but it's all doing the same thing. It has more columns because I include also the original population by age group, deaths by age group, mortality rate by age group, and then after I have these three, I calculate the mortality probability by age group. So let's expose a hypothetical group of people to these mortality probabilities that were estimated based on data from the US in 2010, and let's expose it to their throughout their lives. A hypothetical group of people will experience these rates here. So we have the rates, we got the probabilities in this column generated from the rates. How many people are born in the US? in this hypothetical exercise, 100,000. If I get this chance of dying of people below reaching age 1, and 100,000 were born at the beginning of the period, oh, that's why we need the probability, not the rate, right? Because these 100,000 people here, once they are born, age 0, they're exposed to these chances of dying. So that's why I need the probability, not the rate. The probability is calculating the chance of dying, take into account the denominator, the population at the beginning of the period. So if we have this rate here applied to these people, and these people here are the people alive at the beginning of the age group, is the little lx. See that there is no n here. Why? Only the little lx, because that's the number of people reaching the beginning of that age group. Age 0, age 1, age 5, age 10. So if 100,000 people are exposed to this chance of dying, 612 will die. Just this number multiplied by this. So what we are saying, that there would be 612 babies dying before reaching age 1 if they were exposed to this chance of dying. So this D here is number of deaths in the age group from age X to X plus N. So see, the N is back because the 612 are the people dying from 0 until before they reach age 1. Cool? If 100,000 people are alive, are born, 100,000 people are born, 612 of them die before reaching age 1. How many people will reach exactly age 1? Will reach the beginning of that next age group? 99,388. So this number minus this number is this one here, right? Again, that's why we need probability, because 99,388 are the number of people reaching exactly age 1, the beginning of the next age group. And now we're going to expose them to the probability of dying. Probability, the denominator, is the population at the beginning of the interval. This number times this chance of dying, 106 people are expected to die between the ages of 1 and 4 before reaching age 5. So this case here is the DXN, no, it's D55. No, we are still here. The D14, right? 106 people will die before reaching age 5. This number here, or the number of people who are alive at age 1, 106 of them die between ages 1 and 4. How many reach age 5? 99,281. Expose these guys here to the chance of dying, 57 die. And so here we have the DXN is the D55. The N is the 5, the width of the interval. It's not 4 anymore. And for this group here would be the D10, because it's just age 1. So we do it for everybody until the last age group that everybody dies. So 1,968 people are alive at the beginning of this last age group, reach age 100, everybody dies, mortality probability of 1. So everybody dies in this last age group. Okay? What is the column 5? Is the big LXN. Has that major demographic concept, person years. That's the number of person years lived by the population within that specific age group. So out of this 100,000 people. Not everybody lived all the full 1 year, 12 months. 612 of them died before reaching age 1. Out of the 612, some died in the first months of life. Most of them died in the first months of life. Mortality is higher there. Others died a little older, a few months later. Others died a few months later. But everybody, all these guys here died, all this baby died before reaching 12 months of age. So overall, how many complete years did they live? 99,465. What about these guys here? 99,388. If nobody died here, let's say that 99,388 people reach age 1. If nobody died there, and everybody reached age 5, everybody who reached age 1, let's say that's the same 99,388 reach age 5 here. How much would be this column? Everybody would have lived 4 years. Year 1, 2, 3, 4, until reaching the year 5. So we would have, I just do this here, 99,388 times 4. You would have 397,552. We have less than that because some people died. What about the next age group? If all these people here who reached age 5, let's say that nobody died and everybody reached age 10. You would have 99,281. Now we multiply by 5 because that's the width of the interval. 946,405. It's higher than the 250 here, because here there is no mortality in this example. Here there is mortality. Let's say now, an extreme example, that let's say that there is no mortality at all. This is 0 for everybody here. 100,000 people will reach here 100,000, 100,000, 100,000, everybody. How much would be the big LXN here? If nobody died, nobody dies here. 0 people die because the mortality probability is 0. How much would be this number? 100,000. All these babies in total lived 100 years, 100,000 years. What about this number? How much would it be? 400,000, because all these 100,000 people here would live all the 4 years. What about here? How much would it be? 500,000, because all the 100,000 people here would live all the 5 years, right? So that's what person years is. We are just counting how many years in total those people lived within that age group, right? When we try to get the average age from you guys here, what do? We get how many, what's the age of each one of you now that you completed, and divide by the number of people, the average age. So now here, we have to calculate how many years in total people lived. So how do I calculate the average age? I get all your years of age, add them all, divided by the number of people that are here. This class of 83 people has 8 people, right? But let's get from these 8 people, that's the denominator. Cool? And how do we get this overall number of years that people are living? We pretty much just add up all these numbers here. If I add all these numbers here, that's what I have here on column TX. We have a total of 7.8 million years of life lived by these people. If I add all these guys here, I have this number. If I add from 1 until the last one, I have this number. It's a number of years lived from age 1 and above, from age 5 and above. Total number of years lived from 10 and above. Okay, I have the numerator of my formula. The overall number of years lived by the population. What do I have to divide it by? Number of people. How many people do we have in this population? How many people do we have in this population? How many people at the beginning of the interval were exposed to the chance of dying? 100,000. 7.8 million divided by 100,000, 78.7. That's the life expectancy at birth. So what is the life expectancy at birth is giving us? Well, I got even like goosebumps. It's so cool. Life table. It's if we expose this population here, this hypothetical population, to these probabilities of dying throughout their lives, they will live on average 78.7 years. Quite? And if I get this number of people here, that for those that reach age 1, they live this total amount of years throughout their lives. Add them all. And then divide by the population who reach age 1, we have 78.1. Let's just get one example here that makes it easy to understand. For the 10 to 14, we have this 99,224 people who reach at least age 10. And these are the number of years they lived as a group for each one of these age groups. But of course, some of them died before reaching the next age groups. But in total, they lived how much? 6.8 million years, this number here. If I divide this 6.8 by 99,000, which is the number of people who reach age 10, we have the life expectancy of 69.3. So see that we have a bunch of life expectancies there. It's not just E0. The 69.3 is E10, the life expectancy at age 10. What does it mean, the life expectancy at age 10? If someone reaches the age 10 of 10 years, that person is expected to live an additional 69.3 years. So what's the overall age that those people will have, conditionally that they reach age 10, will be 10 plus 69, 79.3. 79.3 is higher than 78.7. Just to say that these people could have died before they reached age 10, but they overcame the risk of dying, did not die. So they get a bonus. Their average age of life will be 79.3. We can also have a life table that adds this other additional column here. That will be pretty much this number plus the age at the beginning of the interval. So 78.7 is going to be 78.7 because it's 78.7 plus 0. Age 40, for example. Someone who reaches age 40 had the chance of dying before, did not die. How many additional years of life that person is expected to live? 40.5. So that's the life table, right? And what I'm going to show you now is what are the formulas behind these numbers to calculate that, okay? In these next slides here, I'm just explaining one by one what are these columns. We have the age intervals of each group. On column 1, column 2, we have the probability of dying between ages x and x plus n. Column 3 is the number of survivors that reach the beginning of that age group. DXN, number of deaths between the ages of x and x plus n. Big LXN, numbers of years lived by all people who enter the age interval while they are at the age interval. Some people will live longer, will live all the age interval, some people will die there, okay? Number of years lived by the population in the age interval and all subsequent intervals, like all other older age groups, that's the TX. And using the TX and the red X, the little LX, we calculate the life expectancy at birth. And for the other TXs and their other LXs, we calculate the remaining life expectancy at each age, right? Cool. So age groups refers to the range of years between two birthdays. The age group 5 to 9 refers to the 5-year interval between the 5th and the 10th birthdays. So people right before they reach age 10. Probabilities of dying, the most basic column of the life table. And these are probabilities that persons alive at the beginning of an age interval will die during that interval before reaching the next one. So look at this. The mortality probability and number of people dying in that age group divided by the people alive at the beginning of the age group, the little LX. That's why we have probability here. The QXN is a probability. The denominator is the population at the beginning of the interval. For the last age group, everybody dies. Q equals 1. The difference between mortality rates and mortality probabilities is the denominator, as I mentioned. When we get raw data, the population of a country in a specific year by age group, and the number of people who died in that population that year by age group, divided one by the other, this population, usually when we get from public sources, is the population in the middle of the period. Divided one by the other, we get the mortality rate, age-specific mortality rate. And then we make a transformation to get the probability, in which the denominator is the population alive at the beginning of the age interval, and then we do the subsequent calculations in the life table. The little LX is the number of people alive at the beginning of the age interval, known as the little L column. So this term is actually used by demographers. It is calculated by subtracting the number of people dying in that age group from the LX value in the age interval preceding, before the one being calculated. So of the 99,000 people, 224 people alive at the beginning of the age interval from 10 to 14, 70 died. So 99,154 are alive at the beginning of the next age interval at the age 15. So these numbers here are here. 99,224 people are alive at the beginning of this age group. 70 died within this age group. 99,154 are alive by age 15. Okay? Number of deaths. We just, like I showed in the example, we get the number of people alive at the beginning of the age group, expose them to those mortality probabilities. This is an example from the same life table, right? For the group of 40 to 44. This probability of dying, this number of people reaching the beginning of that age group, 966 dying within that age group, this number here. Years lived in the age interval is the number of person years, known as the big L column. which is the total number of years lived by all persons who entered the age interval while they were in that age interval. So for example, out of 98,111 people who are alive at the beginning of the age interval 30 to 34 reach age 30, like I told you guys, if none of them died, how many we would have? This number times 5. Why 5? Because the age group has a width equals to 5 years. We would have 490,055 years. But 539 of them died. So since these guys here died, 488,744, 488,744 is smaller than this number here, right? So demographers assume that deaths are roughly distributing during the 5-year period for many of the age intervals. So how do we calculate the big LXN? For most of the age intervals, we assume that, for example, in that last example, people are dying with the same chances between the ages of 30 to 34, between the ages of 35 to 40. But for the first age groups, for example, 0 to 1 and 1 to 4, those babies and kids who die in those groups, they usually die at the beginning of each one of the age groups. Babies who don't reach age 1, most of them die closer to age 0 than to age 1. Kids who die in the age group of 1 to 4 die closer to age 1 than to age 4. So this assumption of mortality constant within these age groups does not apply for these first age intervals. So that's what we're going to see, several formulas to produce more appropriate big LXN measures for these first year age groups. And we also have another formula for the last open-ended interval, because the last open-ended interval, how many years overall we expect them to live? There are different ways to calculate those, and I'm going to show you here one, and I'm going to give the example in Excel as well. Then we get the years lived in current and all subsequent age intervals, all older age intervals. So the TX is the total number of years lived by the population in the age interval and in all subsequent age intervals. So you pretty much add all the big LX column from that point onto the bottom for all older age groups. That's how we calculate the TX information. So this one here is the T for the age group 95 to 99. And the notation here also doesn't have the N, because we're saying for all those people who reach age 95, how many years they lived in total. So we just get the last two big L columns, big L values, and get the T 95 equals to 29,212. And then we get the remaining life expectancy, the average number of years of life at the beginning, average number of years of life at the beginning of the age interval. If someone reaches that age, how many years will they expect to live from now until the end? The life expectancy at birth is getting for everybody. We expect that if people are exposed to this chance of dying here throughout their lives, 78.7 years. If people reach age 25, how many additional years they would expect to live? 54.7. 54.7 plus 25 have 79.7. 79.7 is higher than this. So we get a bonus by surviving to older ages, right? You're just getting the TX column and divided by the LX column. And this is the column that was not in the table that I showed you, the average age at death. The EX is the expectation of future life beyond age X. It's not the average age at death. We add X, which is the beginning age of that age group, to the life expectancy in that age group to obtain the average age at death for cohort members who survive at least until the beginning of that age group. Not all life tables include X plus EX, but we can add them. And this X plus EX always goes up because people, you gain bonus as they get older. And the EX not always go down. It often go up after the first few years of life because babies who survive infancy are no longer subject to those really high risks of infant mortality. So in some cases, we see that life expectancy, the column of life expectancy going up at the beginning from the first to the second age group because of the high levels of infant mortality. Okay, so we'll continue on this chapter, on this section on Tuesday. On Tuesday we will cover whatever we can here on this chapter about mortality. And then on Thursday, 1 week from now, we have exam 3. Okay? And exam 3 will take into account at least until life tables. So be prepared for that. That's usually the topic that people have more trouble. And I will focus more on the formulas on Tuesday. So just come prepared and study more of this subject. Okay? Thank you very much. Have a great weekend. And I see you guys on Tuesday.